Okay, so now we're going to talk about this concept of optical activity. So what the heck is that, right? So as we said before, when you have two stereoisomers, the vast majority of their physical properties are the exact same. Melting points are the exact same. Boiling points are the exact same. Solubility properties are the same. Intermolecular forces at work are the exact same. Even things like heat of combustion are going to be the exact same, right? So there are very few physical properties that we could test that would distinguish between two stereoisomers. One of the things that we can use is this idea of optical activity, okay? So first of all, we got to talk about light for a hot second. Light is made up of waves, right? You have electromagnetic waves, which is what a photon is. It's an oscillating electromagnetic field. When you turn on the light bulb or whatever, these waves are all oriented in different directions, right? You have a mixture of every different possible orientation. So some of your waves are coming at you like this, other ones like this, and then everything in between, right? So that's what this represents over here, is this idea that a light source generates light that is what's called now polarized, meaning it contains all different directions of its waves. Then you put it through a filter. This is a special polarizing filter. And what that does is filter out all of the light except for one that's coming in one direction, right? So it's coming out of the light source and it's coming here, 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 here. And then it goes through this filter and the only one that's left is the one that's straight up and down. This is what's called polarized light. If you have fancy polarized sunglasses, this is what they're doing. They're filtering out the vast majority of light using one of these special gradients. So the only thing that's coming at you is light that's a specific direction. Okay? What we're gonna see is that chiral compounds can rotate this plane polarized light, okay? So optically active is the same thing as saying chiral. All right, so how would this sort of experiment look? So again, first of all, you have this light source that's got all the different directions, all different polarizations. You put it through this filter here and you get just one direction, your polarized light, okay? Then you're gonna pass that polarized light through your sample. So in this tube right here contains your sample of whatever compound you're talking about, all right? And if you have just a pure enantiomer, for example, just the R enantiomer of a compound, what's going to happen is that light is going to rotate as it's going through your sample. And when it comes out at the other end, you can measure the degree to which it's rotated. Okay? Chiral molecules are the only ones that are going to rotate light like this. Achiral molecules are optically inactive and they will not rotate light. All right, maybe one molecule rotates it a little bit in one direction, but then it's going to hit another molecule and that's going to kick it back the other direction. So all these things will cancel out and you'll just get your straight up and down light at the end of it. Okay, so only a sample of pure enantiomer is going to be optically active. Okay, we measure the degree to which something is optically active. And we call it that compound's specific rotation. So this is actually the angle at which it rotates light. So for example, 2R2 butanol might have a specific rotation of negative 15.0 degrees. Meaning that when you took that sample of pure 2R2 butanol and put it in your polarimeter tube and did this experiment, it came out and it rotated that light in such a way that, did I say negative or positive? Okay, sorry, not to be confusing. This is the negative direction. It rotated that light in such a way, and then we can measure it, right? So that's this whole deal, is that we have most of our physical properties are identical for a set of enantiomers. This is one example of something that isn't. When you see these specific rotations reported, you'll see them reported with a temperature and a wavelength as well, because they do depend on that sort of thing. They also depend on concentration. So standard would be 1 gram dissolved in 1 milliliter of solution through a fixed path length of 1 decimeter. Okay, so these are these conditions that we use to standardize so that we can compare things very easily. So again, R and S refers to your different stereocenter designations, right? These are chiral molecules, they're enantiomers, mirror images, and they will rotate light to the same extent, but in different directions. So the specific rotation for 2R2-bromobutane is negative 23.1, whereas for the S stereoisomer, it's positive 23.1. Okay, the 20 refers to the temperature at which this is taken at 20 degrees, and the D, this is the wavelength. It refers to just a special lamp, the sodium D line. I wouldn't worry too much about that. Bottom line is it has to be done at a specific wavelength. Okay. When light is rotated in the positive direction, we call that dextrorotary, or refer to it as the D isomer. D stereoisomer. When it rotates light in the negative direction, it's levorotary, and we refer to that as the L. Okay, so up at the top here, this would be the D, and this would be the L stereoisomer. There is no way to predict the magnitude or the direction of optical rotation just by looking at a molecule, right? So the fact that this right here is negative 23.1, nobody knew that off the top of your head. You have to stick it in the machine and take the measurement, okay? There's also no relationship between R and S and D and L. Well, sometimes an S enantiomer will rotate it in the positive direction, sometimes an S stereoisomer will rotate it in the negative direction. Okay. Now this is another vocabulary word, which is a racemic mixture. So when you have a racemic mixture, that is a sample that has equal amounts of your two enantiomers. So if I had a 50-50 mixture of R and S, those would be optically inactive. They would not rotate plane polarized light. To the extent that you have one isomer rotating light in one direction, you have another isomer that's counteracting it, rotating it in another direction. So the net effect will be zero rotation. But that is what a racemic mixture means. It means a 50-50 mixture. Okay. We can calculate, well, so first we're going to learn about enantiomeric excess, which is going to be used, we'll sort of plug this into this whole optical rotation business in a second. But first of all, let's just figure out how to calculate enantiomeric excess, given that we have a sort of 70-30 mixture in this case. Your enantiomeric excess calculation is going to be the amount of D isomer minus the amount of L isomer divided by the amount of D isomer plus L isomer. And this is you take the absolute value. So it really doesn't matter which one's the D and which one's the L. You can think about that as R and S as well. But so what we're going to do is we're going to take our 70 minus 30, take the absolute value of that. $70 times 30 times 100. And so what we would see is in this particular distribution, we would have an enantiomeric excess of 40%, right? So I have 40% more R than S. And so what we're going to see is if we took this mixture and we stuck it in that same instrument, it would indeed rotate light in this same direction of the R configuration, just not to that full extent, not to that 23.1. All right, so now let's do an example where we have some sort of a mixture and we've stuck it into our polarimeter and seen that it rotates light, but just not to the full extent, right? So here we have a mixture. Again, this is my R isomer, this is my S isomer. If I had my pure R, it would rotate light negative 23.1 degrees. If I had my pure S, it would rotate light positive 23.1 degrees. But I have a mixture, and I don't know how much R and S there is in there. That's what we want to figure out. But I stick it in this machine, and it rotates light positive 4.6 degrees. So first of all, which compound do you think it has more of? Should be the S isomer, right? Because this is positive and this is positive. Okay, so something to keep in mind. Just like we calculated enantiomeric excess before, we can calculate it using these values here, where the observed optical rotation divided by the optical rotation, the specific rotation of this compound when it's pure, times 100 will give us that same percent enantiomeric excess. So here we take our 4.6 and we divide it by, and again, these have absolute values, so it doesn't really matter which one you choose. We can choose negative 23.1 if we want, but because it's going to take the absolute value, make it positive. So this gives you like 19.9, we're going to call it 20. An enantiomeric excess of 20%. Okay, so then I can plug it into this formula here and work backwards to figure out that that means that I have 60% S stereoisomer and 40% R stereoisomer. And you can do this calculation kind of quickly. If you're good at algebra, you can rearrange the equation on the other side and solve. That's all well and good. But 60 minus 40 is that 20%, right? So that's the enantiomeric excess, is the difference between those two. So that means I have a 60-40 distribution of S stereoisomer to R stereoisomer, right? So that's what we can use this optical rotation to measure.